So I will wait for 5 minutes and then I will start the session. Am I audible?
Yes.
Okay. So let's start the class. So we'll start the class with some examples. So last class I talked about different types of composites, right? So what are the composites? What are the parts of the composites? The reinforcement matrix. So I have some examples. So actually, I'm right now working from my lab. So I have some samples to show you about composite. So like here you can see this is a composite made of epoxy and glass fiber mat. So by the design you can see these are mat structure. So this is the reinforcement glass fiber mat and epoxy is used as the matrix here in this sample. Whereas this is a glass fiber chopped strand mat. So you can see there are chopped strands of glass fiber. They are so these are the reinforcement and the matrix used here is epoxy. And there is, as I said, there are three types of reinforcement mostly used: glass fiber, carbon fiber, and aramid. So this is an aramid fiber mat. As you can see, this is not a composite. This is only the reinforcement. So this is aramid fiber mat. And then we have this is a composite made of carbon fiber. So these are, as you can see, these are in the form of mat, and there different layers of carbon fiber mats are used as reinforcement, and they are combined by epoxy that makes this composite. So this is very hard. It has a very good mechanical strength. And this one has also carbon fiber, but these are fibers, and they are also made composite by using epoxy. So these are some of the examples that I had here in my lab, so I could show you to have little bit visual understanding of what we studied last day and what so I taught in the first set of lectures. So I will start my presentation. Is it visible?
Yes.
So okay. So welcome to the course Mechanics of Fiber Reinforced Polymer Composite Structure. Today is the live interactive session in which we are going to do some sample problems based on assignment number 2. I am Ananya Mandal, TA of this course. So before moving forward with the assignment, sample questions for solving assignment number 2, let's recap whatever concept is required for solving this assignment number 2. As it has already been taught by sir in his lectures, and this is a screenshot directly from that lecture. So the main basic introduction that is required for solving the questions are that the stress and strains that we have to consider when we are considering a composite. So initially we talked about composite, how they are formed. Then one layer of composite that contains one reinforcement matrix makes a lamina, and a stack of laminas makes a laminate. So first we will study a single lamina, the different components of the lamina. So we will be first focusing on the micromechanics. So in micromechanics we talk about the stress and strain. So suppose you can see on the screen, we take a small portion of any part like reinforcement or matrix anything or and we put a force on that small unit. So that force will have three types of stresses and three types of strain. So as stress is directly proportional to strain, and that proportionality constant is known as the elastic modulus. So here there will be the 3D stresses and strains. So if there is a stress in like x direction, so there will be strain in xy direction and xz direction. Similarly, if there is a stress in y direction, there will be strain in yz and yx and like that. So that will give us 9 types of stresses and 9 strains. So what are the 9 stresses? The 9 stress are stress that you will be seeing later. Stress 11, 22, 33, 23, 31, 12, 32, and then shear stresses. So there are three direct stresses, normal stresses, X, Y, Z, and 6 shear stresses. And with in respect to that stresses, there are strains. So they are directly proportional to each other. Now we get 9 stress components and 9 strain components. Of that, we have equality of cross shear symmetric stresses and strains. What does that mean? That means when there is a stress, when there is a shear stress in xy direction, it will be equal to the stress in yx direction also. So similarly, when there is a stress, shear stress in yz direction, there will be shear stress in zy direction equal, and for zx direction, it will be equal shear stress in xz direction. So this is what sir taught in class, and the relation between the stress and strain. So suppose there is we have to find the amount of strain that occurred in only x direction. So the first term shows the strain occurred because of stress in the x direction, but that's not the only stress that causes the strain in x direction, but also the strain that occurring in y and z direction affects the strain in x direction. So that considering those formulas, we can get the overall strain in x, y, z direction, and the shear strain can be equal to the shear stress divided by the shear modulus. So this is like the basic equations, and sir taught about this in the class. Now let's go to the sample questions. So the first question is, in generalized Hooke's law, sigma iz equal toCijkl eta kl. So here the stress equal to a constant into the strain, where ijkl equal to 1, 2, 3. So what is Cijkl is? So the options are A, second order tensor, option B, fourth order tensor, option C, 6 cross 6 compliance matrix, or option D, 6 cross 6 stiffness matrix. Now as I said here, that there are 9 stress components and 9 strain components according to this. Now this 9, suppose we consider the stresses. So there are 9 stresses. For 9, the matrix between this 9 cross 1 with the strain in 9 cross 1, we will get this whole matrix, that is 9 cross 9. So this is the stiffness matrix. So the stiffness matrix relates the stress with the strain. So for a certain strain, when we multiply it with the stiffness matrix, we can get the value of stress. And similarly, there is a compliance matrix, which is where strain is equal to compliance matrix into the stress. Okay, so this is what the generalized Hooke's law talks about. So here you can see the stress, there are 9 components, it will make a matrix of 9 cross 1. And the strain has also 9 components, matrix 9 cross 1. So for these two matrices, the stiffness matrix has 9 into 9, 81 components. So this 81 components shows the relation between these 9 stresses and 9 strains. Now, when there are 9 components in one matrix, it is known as second order tensor, because the 9 is equal to 3 to the power 2. So any matrix we consider as in form of 3 to the power of what is its tensor form. So if it is 3 to the power 1, it will be vector, 3 to the power 2, it will be second order tensor, and like that in 9 cross 9 matrix, it will equal to 81, which is equal to 3 to the power 4. That's why it is called as the fourth order tensor. So this is the answer for the first question. Now the next question is, match the following, where first table talking about the type of material and the second one talks about number of independent elastic constants. So the types of materials are isotropic, anisotropic, monoclinic, orthotropic, and number of independent elastic constants are given as A21, B9, C2 or D30, and we have to match them. So when sir taught us in a class about the different number of independent elastic constants, so first thing as from the general Hooke's law, we know there are 81 independent elastic constants. From this table you can see. So these are 81 terms that are showing the relationship between the 9 stresses and strains. But then comes the shear symmetric concept that I showed here. The equality of cross shear symmetric stresses strains makes it 6 components, because half of the stresses are similar to the other half. So we will only consider one of them. So that will be 3. And there are 3 normal stresses, that will be 3, that will be equal to 6. So from that, we will have 6 types of stresses and correspondingly 6 types of strain. So in this stiffness matrix, we will have 36 independent elastic constants. So from 81, it came to 36. After 36, we consider a symmetry. As you can see, the stiffness metric constants, which shows C12, it will be equal to C21. That is according to the first law of thermodynamics. As we consider the work per unit volume of two types of stresses, we can see that the constants are symmetric. So C12 will be equal to C21, C13 equal to C31, like that. So the lower portion will be symmetric to this upper portion. So that will decrease the independent number of elastic constants to 21. So that signifies the anisotropic system. So the anisotropic means that the property of a material which allows it to change or assume different properties in different directions. So anisotropic generally means that in every direction there will be different properties. So we have to consider all the stresses and strains in all of these directions. So that's why for an anisotropic system, the number of independent elastic constants will be the highest, that will be 21. So we can match number 2 with A. Now, after anisotropic comes the condition of monoclinic. So monoclinic says that the elastic solid has one plane of material property symmetry. That is, suppose we had a material in all the 3 directions, it was not, there was no symmetry. They were all independent. Suddenly we consider one plane to be symmetric. So suppose the plane xy is the plane of symmetry. So in z and z dash direction, all the properties will be similar. So that is known as a monoclinic system. So in monoclinic system, the number of independent constants decreases further and becomes 13. So all these derivations are already showed in the class. I am directly taking the number of independent constants that will be for different cases. So for monoclinic, it will be 13. Now in monoclinic, we consider that there is only one plane of symmetry. So next is orthotropic, where we consider that there are 2 planes of symmetry. Now if there are 2 planes of symmetry, then the third plane will also become symmetrical. So orthotropic is when all the 3 planes of material property are symmetric. So in that case, the number of elastic independent constants will decrease further and become 9. So for orthotropic, it will be 9. Now after orthotropic, there is another type of material that is transversely isotropic. So in that what happens, it is an orthotropic material, but one of the planes is isotropic. So suppose in there you have a body, and in all the symmetrical directions the properties are same, but also one of the face of that body, the whole property will be same. Suppose the direction 2 and 3, the plane which gives you the direction of 2 and 3, so that will have a isotropic surface. So any properties like C12 will be equal to C13. C23 will be equal to C32. So 2 and 3 will be interchangeable. So that means they are dependent to each other. So we can remove one part of that, and that will become lesser independent elastic constant. That for transversely isotropic there will be 5. And the last one comes isotropic, where the properties are similar in all the directions. So here only 2 independent elastic constants are required, that is the modulus and the Poisson ratio. So properties remain the same in different directions. Isotropic material have only 2 independent elastic constants, that is the Young modulus and the Poisson ratio. And the shear modulus has an equation which is related by the Young's modulus and Poisson ratio. So we can find all the 3 engineering constants that are required for finding out these independent elastic constants. Okay, so from that we can match all the our options. So first was, so it is easier for you to remember the number of independent elastic constants with respect to what type of system we are talking. And there is this stages in which number of independent constants are decreasing. So it's easier to remember that first it will come anisotropic, which will have 21 independent constants. After that, there will be monoclinic with one symmetric phase that will have 13 independent elastic constant. After monoclinic, which has one symmetric plane, there will be orthotropic with three symmetric planes. It will have nine independent constants. And finally, isotropic, which only needs two independent elastic constants. So by matching this, we get the option B as our correct option. You see, one is C, 2A, 3D, and 4B. Okay. So the derivation, how this number of independent constants is found is already sir taught in class. So I am not taking them. I am directly using the final values. So the next question is question number 3. In the stress-free relation of a fully anisotropic material, which one of the following is true? Option A, all the extension coupling terms are 0. Option B, all the shear extension coupling terms are 0. Option C, all the shear coupling terms are 0. Or option D, all the extension, shear and shear extension coupling terms are non-zero. So what are these terms? This extension, shear extension and all. So you can see this is a anisotropic compliance matrix. So compliance matrix gives a relation between the strain and the stresses. So here, if there is a certain stress that is sigma 1, so the relation with sigma with eta I, the strain in direction 1 will be equal to S11 into the stress in direction 1. So these are directly related to each other. So eta 1 equal to S11 stress in one direction, strain in direction 2 equal to S22 into the stress in direction 2 and so on. So as these are directly related to the stress in the given direction, so these are named as the extension part. Now next is the extension coupling. This is when the stress in one direction is related to the strain of the other direction. As you can see, S12, here the strain is in direction 1 and stress is in direction 2. So that type of independent constants are called the extension coupling. And the next is the shear. So as extension, the shear are the independent constants which relates the shear, stress and strain directly to each other. And next is the shear coupling, which gives us the relation between the shear stress and shear strain in different direction with each other. And lastly, shear extension coupling, where the shear extension coupling, the strain is related to the your strain is related to the shear components. That time we use the shear extension coupling. So these are different parts of this matrix that are named and distinguished. So now let's see what they are asked in the question. So they have asked, for a fully anisotropic material, which of these conditions are true? So as you can see, this is a fully anisotropic material compliance matrix. It can be also written like this in terms of stiffness matrix. So in the anisotropic material, all these independent constants are non-zero because there is certain values, as all the properties in all the directions are different. So there will be some value relating the stress strain in all these directions. That's why all the extension, shear and shear extension coupling terms will be non-zero. So that will be the correct answer, option D. So this is for a fully anisotropic material. Now question number 4. The same kind of question, but here they ask in the stress strain relation of an orthotropic material, which of the following is true? So here you can see this is a stiffness matrix of an orthotropic material. So stiffness matrix and the compliance matrix can be interrelated by just doing the inverse of it. But the portions which are showing 0 will remain same. So how these portions became 0, that the derivation is already shown by sir in the class. But you can directly relate the stiffness or compliance matrix of an orthotropic material. And from the known these sections, you can relate what they have been asked in the question. So option A, they are saying that all the extension coupling terms are 0. So these are the extension coupling term S12, S13, S23, or in stiffness matrix like C12, C13, C23. So these don't look like 0. So this answer will be not correct. Next option is all the shear extension coupling terms are 0. Shear extension coupling terms are these ones. So this one you can see this whole matrix part is 0. So this option is correct. Next option is all the shear coupling terms are non-zero. Shear coupling terms are these ones S44, S55, S66 or C44, C55, C66. So these terms are non-zero. So all the shear coupling terms are non-zero. So no, sorry. So these are the shear terms. This is the shear coupling terms. So these are all 0. So this option is also incorrect. And lastly, all the shear and shear extension coupling terms are non-zero. But here you can see the shear coupling terms are 0. That's why this option is also not correct. So our correct option is option B. So in the assignment number 2, you have to first see which material they are talking about. Find out the compliance or stiffness matrix of that material, or you have in the for the final exam you have to remember which all terms are getting cancelled for these different types of material. So accordingly, you can compare it with this diagram where they show different regions of this matrix, and you can find the answer of these questions. Now this is a similar question where they are talking about an isotropic material, but here we have to find which of the following is not true. So this is a stiffness matrix of an isotropic material. So we will relate this with this table. So the first option says that all the extension coupling terms are 0. So these are the extension coupling terms. You can see these terms are non-zero. So this is not correct. Next is that all the shear extension coupling terms are 0. So the shear extension coupling terms are these ones. So these ones are 0. Shear coupling terms are non-zero. Shear coupling. So these are the shear coupling. So these are also 0. So this is also not correct. Sorry. All the shear coupling terms are non-zero. Which is non-zero. But these are 0. So this is a shear coupling. And non-zero. So this is a correct statement. So this will also not be an answer. And all the extension, shear, and shear extension coupling terms are non-zero. So this is also not correct. And this is also not the answer. So our answer will be option A, that all the extension coupling terms are 0, which is the only non-true statement. So we have to see what they have asked, either to find the true ones or the non-true. So we have to find the opposite one. So here, this is the incorrect one here. That will be the answer. So the next question is, in the stiffness matrix and compliance matrix, the diagonal terms are, options are A, are always negative, option B can be negative or positive, option C must be always positive, or option D, all positive is C and negative for S. Now the stiffness matrix C, and we have to talk about the diagonal terms. So these are the diagonal terms. Very bad. Okay, sorry. So these are, as you can see, these are the diagonal terms. So basically, what is the significance of diagonal terms? It directly relates the stress to the strain. Suppose there is a stress in direction 1, it will be directly related to the strain in the direction 1 by this diagonal term C1111. Similarly, the stress in direction 2 is related to strain in direction 2 by this diagonal term C22. So all these diagonal terms are always directly relating one stress to the strain. Now, if there is a stress in certain direction, like in one direction there is stress, positive stress, so the strain in that direction will also be positive. If both the stress and strain are positive, then their the modulus will also be positive. So but this compliance stiffness matrix or compliance matrix basically signifies like a relation between stress and strain. So if these two terms are positive, then the coefficient relating these two will also be positive. So that's why always the diagonal terms will be positive. So our answer is option C. As you can see in the statement, if displacement is given at a certain node, then the action at that node should develop in the direction of the displacement. That's why the mean diagonal elements in stiffness matrix is always positive and cannot be negative at all. So any doubts till now?
No, ma'am.
No, ma'am.
Okay. Okay, then I will continue. So these parts are from the next lecture. So question number 7. For an isotropic material, the Poisson's ratio mu is bound as. So options are A -1 to 1.5, option B -0.5 to zero point 0.5, option C 1 to 2, or option D -2 to -2. So this is one of the slides that is already taught in the class, which shows the restrictions on engineering constants. So what are the restrictions on the Poisson ratio? So for an isotropic material, the shear modulus and elastic modulus has to be always positive, and the relation between the shear modulus, Poisson ratio, and the elastic modulus is this. So as G and E value has always to be positive. For that, the mu value will always be greater than -1. So this is one of the limits of Poisson ratio. The next is, suppose there is an object made of isotropic material and is subjected to hydrostatic pressure. So hydrostatic pressure, according to Pascal law, it says that there is a body in the water, so pressure in all the directions will be equal. So that talks about the hydrostatic pressure of that object. Now, here when we talk about the bulk modulus of that substance, so the equation, the formula for bulk modulus is equal to minus V dP by dV. So it gives the relation between pressure and volume. So as you can see, if the pressure on that object will increase, the volume will decrease. Similarly, if the pressure releases, the volume will increase. So these two are opposite to each other. So anytime dP by dV value will be negative, and that negative will make the modulus as positive. So this modulus value will always be positive. Now there is a relation between the bulk modulus, elastic modulus, and Poisson ratio. So this is that relation. So from this relation, considering that K and E both need to be always positive, the value of mu has to be always less than 1 by 2. So this restrictions comes directly from the correlations between different engineering constants. So we have already these two engineering constants, which gives a relation between the bulk modulus and shear modulus in terms of elastic modulus and Poisson ratio. So from these two equations, we can find this range between which the Poisson ratio should be. So you can see the Poisson ratio has to be more than -1 and less than 1 by 2. So this to ensure the shear or hydrostatic loading does not produce negative energy. So this is the range in which the Poisson ratio has to be bounded. So that is our option A. Okay. So question number 8. A transversely isotropic material has three orthogonal planes of materials, property, symmetry, and options are A. Two of them are planes of material property isotropy. Option B. One of them is a plane of material property isotropy. Option C. All three of them are planes of material property isotropy. Or option D. None of them are planes of material property isotropy. So the definition of transversely isotropic material says that when we discuss that initially we consider an orthotropic material. So orthotropic material has three symmetry faces. So in all the three directions there will be symmetry. Now comes the transversely isotropic material in which it is already orthotropic, but along with orthotropy one of the face is isotropic. That means all the properties around that face will be similar. So orthotropic materials with one transverse plane of symmetry where material properties are independent of direction, a plane of isotropy, is called a transversely isotropic material. As you can see, this is an orthotropic material. In this, that means in all the directions the properties will be same, and one of the faces here, this face is between the axis 3 and 2. So this is isotropic. So any properties that will be in the direction of 3 will have the same value that will be the properties in direction 2. Suppose the stress, suppose the independent constant we take as 3, 1. So that will be equal to 2, 1 also. So we can interchange the values which considers these two axes. So that is an example, that is what transversely isotropic material does. So from the definition, option D is our answer. That is, it has one of the transversely isotropic material have three orthogonal planes of material property symmetry, and one of them is a plane of material property isotropy. Okay. The next question is question number 9. That with respect to Cartesian coordinate x, y, z, the state of stress at a point in an orthotropic material is sigma x not equal to 0, and the stresses in y, z, and shear stress in xy direction, yz direction, and xz direction is equal to 0. Then the strains induced will be. So this is like solving the matrix form. So for orthotropic material, this is the matrix for the compliance matrix. So here it is giving us the relation between the strain and the stress by this independent constants. So what is given, the condition given in the question, that the stress in x direction, or you can say one direction, is not equal to 0. That means this term is non-zero and all the other stresses are 0. So these all terms will be equal to 0. Now we have to find what all strains will be induced in this system. So we have to find the correlation between this stress and which all strains we can find from the compliance matrix. So strain in one direction, that is in x direction, is equal to S11 sigma 1. So S11 value is non-zero. So we will get the strain in direction 1. First strain in direction 2, S12 value is also non-zero. So we will get the strain in direction 2. And for strain in direction 3, S13 value is also non-zero. So we will get this value also. Now comes shear stress, shear strain in 2, 3 direction. So here the coefficient is equal to 0. So the relation between these two, there will be no relation as the independent constant is equal to 0. So this value will be equal to 0. Similarly, as all these coefficients are 0, so this is shear stress, shear strain in all the directions will be equal to 0. So for solving this question, first thing you have to see is what material they are talking about. After you found the material, you will have to remember or understand the what will be stiffness or the compliance matrix according to what relation they have asked. They can even ask, like, give the value of strain and find which of the stresses are induced. So for that you have to use the stiffness matrix. Here we are using the compliance matrix because the known value here is the stress and we have to find the strain. So from that you can see the strain in x, y and z direction will be non-zero and the shear strains will be all equal to 0. So you have to choose which of the answer goes with the solution. So option C, you can see all these strains in all the three directions is non-zero and the shear strains are equal to 0. So this is our correct answer. Similarly, like the last question, there we use orthotropic material. Here they are talking about an isotropic material. With the same condition that the stress in x direction is non-zero and all the other stresses are equal to 0. So we will cross all the stresses. So this is a compliance matrix for an isotropic material, but the coefficients I have written in terms of the engineering constants. Okay, so here again we have to see which all strains we can get. So this coefficient is non-zero, so we will get the strain in x direction. This is non-zero, we will get the strain in y direction, and this is also non-zero. So we will get the strain in z direction also. But these three are 0, so we will not get any shear strains. All the terms of shear strains will be 0. So our answer will be option D. Here, the strain in x, y, and z direction are non-zero, and the shear strains are all values equal to 0. The next question is question number 11. So, orthotropic materials are characterized by option A, 3 Young's moduli, 3 Poisson's ratio, and 3 shear moduli. Option B, 6 Young's moduli and 3 Poisson ratio. And option C, 6 shear moduli and 3 Poisson's ratio. Or option D, 3 Young's moduli and 6 Poisson's ratio. So, Young's modulus, Poisson ratio, and shear modulus. These are engineering constants. So, engineering constants uh, are like the relation between the stress and strain. The Young's modulus gives us the relation between the stress and strain in that direction. The shear modulus gives us relation between the shear stress and strain in certain direction. And Poisson ratio is equal to the ratio between the transverse and the longitudinal stress. So, the elastic constants which form the stiffness matrix are not directly measured from laboratory test on a material. One can measure engineering constants like Young's modulus, shear modulus, and Poisson ratio from laboratory tests. The relationship between engineering constant and elastic constants of stiffness matrix is also not straightforward. This relation can be developed with the help of relationship between engineering constants and compliance matrix coefficients. So all these coefficients have some relation with respect to this Young's modulus, Poisson ratio, or shear modulus. As I think I have shown previously. Here, as you can see here, the stress in x direction is in relation with the strain in x direction, and this comes as the coefficients of the compliance matrix or stiffness matrix, and this is in terms of a modulus. So this is a Young's modulus. Similarly, this is Poisson ratio, and these are shear modulus. So all these independent constants are come by a certain relation with all these engineering constants. So there are 3 Young's modulus, 3 Poisson ratio, and 3 shear modulus. So which defines all these values of the stiffness and compliance matrix. And these values can be calculated by using a UTM that already sir talked about in class. And maybe later after this session, I can actually show you a UTM we have here and show how things, not by work, I can only show how things work and how we can find different Young's modulus, Poisson ratio, and shear modulus. Okay, so answer for this question will be the orthotropic materials are characterized by these 3 Young's modulus, 3 Poisson ratio, and 3 shear modulus. So option A is the correct answer. So the last question is that a specimen made from an orthotropic material is tested along perpendicular directions 1 and 2. 1 and 2 are the planes of orthotropy in UTM. To obtain Young's modulus, Poisson ratio, and the following data were obtained, where E1 is equal to 200 gigapascal, E2 20 gigapascal, and Poisson ratio mu12 is equal to 0.3. We have to find the possible value of mu21. So from the relation between the relation of symmetry, that the independent the independent coefficients of the compliance or stiffness matrix. We already know that Sij is equal to Sji due to symmetry. So putting the values in this relation, we can get a relation between Poisson ratio and modulus. So this is the relation where mu21 by E2 equal to mu12 by E1. This is easily derivable. So you have to remember this equation, as in many questions directly this equation can be utilized. So it is better to know the relation between the Poisson ratio and the modulus. So this is the relation mu21 by E2 is equal to mu12 by E1. Now we have already given the value of E1 200 gigapascal, E2 20 gigapascal, and mu12 this value as 0.3. And they are asking for the value of mu21. So putting those values in this equation, we can get the final answer. That will be option A, 0.03. So this is a very simple numerical with one of the relation already shown in the class by sir. Any doubts?
Ma'am, for that
Yes.
last question, could you show that again? Just the question.
Okay.
And here, this relationship is applicable only for orthotropic, or it depends on the. We know for orthotropy that minus mu upon E is the sort of in that uh, extension coupling section, right? That's why we
Yes.
know that. Yeah, so S12 and S121. So that's where we have equated them.
Hmm.
So similar
Extension
questions
coupling term.
for, yeah. So for similarly for different types of material, similar equations we need to remember sort of for exam, or like similar questions may be asked, but for not orthotropic material, but for other types. Is that possible?
Hmm.
Where nu and e or sort of similar values are given, but it's not just nu minus nu upon e for other materials. It's more complicated or something similar.
Um, for all the materials, not orthotropic. Any if you even if you go
Okay.
for isotropic materials, so
Okay.
S13, S12, these have their relation with the engineering constants. So
Okay.
here uh, this the law of symmetry goes for all the materials, anisotropic also. So from anisotropic only it started. Initially we have 81 independent constant. We use the shear
Right.
symmetry and then symmetry. So that point where we use the symmetry, we use starting from anisotropic. So any material, all the materials, anisotropic, transverse anisotropic, all of them, the law of symmetry will applicable. So wherever there will be law of symmetry applicable, this equation will be applicable.
Okay. Thank you.
Any doubts from the questions I discussed or from the class lecture? Okay, so any of you has actually seen a UTM or worked with an UTM, Universal Testing Machine?
Yes.
Okay.
Yes, ma'am.
Yes. So you know how to find the like modulus and Poisson ratio and shear modulus in UTM?
Yes, ma'am.
Okay. So actually, right now next to me, I already have an UTM here. Maybe you guys have also worked with an UTM like this. So mostly modulus, we there are attachment different. Okay. So this is an UTM. It has these kind of attachments which are used for testing. Can you see?
Yes,
Yes,
ma'am.
ma'am.
So these are the attachments. So whenever we have like a sample, so this is a composite sample, suppose we attach this sample between these two hooks, and we can we one of this will be remaining stationary, and this will be pulling this sample up. So that from that we can see what will be the longitudinal stress, and because of that we can find the modulus. And for finding the Poisson ratio, there is another different attachment. So that attachment will be attached to this in a transverse direction. So there will be a longitudinal pull, and from the change in the thickness in the transverse direction, we can find what is the Poisson ratio. And also for shear modulus, these attachments can be changed, and those are like round attachments which when some like suppose this is kept between them, so both this attachment will rotate, and from that we can find the shear modulus. So it mostly UTM has many attachment according to our requirement. So this is like an UTM which is used for finding out those engineering constants. Uh, okay, so any doubts from the class or the assignment sample question, or any doubts in solving the assignment number 2, you can ask.
No, ma'am. Thank you.
Okay, then next class I will be discussing the sample problems for assignment number 3. So if you have any doubts in the lecture or any problem while solving assignment number 3, we can discuss in the next class.
Thank you for showing the real materials, actual examples.
Okay, thank you. Actually, last class I was not able to do the session properly, but this time I did it in the lab. So my lab had all the samples, so I was able to show them. So it was like
Thank you.
visual examples. Okay, then I will end the session here. Maybe I will wait for some more time. If you have any doubts, you can stay or you can leave. Because the session is for 2 hours, I will be waiting. Maybe someone comes late. Okay, thank you.
हेलो मैम।
Yes,
हेलो
yes.
मैम, जो हम टेंसाइल के लिए या फ्लेक्सुरल स्ट्रेंथ के लिए हम स्पेसिमेन कटिंग करते हैं, वो भी कंपोजिट के लिए, जो क्योंकि मैं नेचुरल फाइबर पे काम कर रहा हूँ मैम,
हाँ,
तो
हाँ।
मैम उसका जो सैंपल कटिंग है वो जैसे टेंसाइल के लिए कोई सैंपल कटिंग करना है मेरे को, तो वो कैसे करेंगे मैम?
उसके
तो
आईएसओ
कौन सा
स्टैंडर्ड्स
स्टैंडर्ड
होते हैं।
फॉलो करेंगे, कैसे करेंगे?
अकॉर्डिंग टू योर नीड, एक्चुअली कॉम्पोजिट का अलग स्टैंडर्ड होता है, एंड तुम्हारे पॉलीमर का अलग स्टैंडर्ड होता है। सो मोस्टली डॉग बोन सैंपल्स बनाते हैं कॉम्पोजिट के, विथ आई थिंक कितना लेंथ होता है एंड थिकनेस अराउंड 2 mm और 4 mm देते हैं। सो वो एक बार टेंसाइल टेस्टिंग का वो देखना पड़ेगा, आईएसओ स्टैंडर्ड क्या है। हाँ, ठीक है, मैं एक बार चेक करके बताती हूँ, ठीक है, एक मिनट।
मैम। हाँ जी मैम,
हाँ हाँ बोलो।
पूछो मैम। जैसे मैं अगर मैं नैनो कंपोजिट बना रहा हूँ तो वो कोई नैनो कंपोजिट का सैंपल बना रहा हूँ, तो उससे मैम उसकी कटिंग, मतलब कटिंग, जो सैंपल कटिंग की क्या प्रोसेस यूज करूंगा मैम, कटिंग के लिए मतलब,
नैनो
कट नहीं
कॉम्पोजिट
हो रहा
के
मतलब कोई मशीन से या कैसे?
नैनो कॉम्पोजिट का तो मेरे को उतना आइडिया नहीं है, मैंने कभी नैनो कॉम्पोजिट के साथ काम नहीं किया है, नॉर्मल कॉम्पोजिट से काम किया
जी
है। आई थिंक जो सर है,
मैम, तो
अ,
नॉर्मल कंपोजिट की। हाँ जी मैम।
जिन सर का
क्या बोल रहे थे
कोर्स
मैम
है ये,
सर?
उनको आप मेल कर सकते हैं अपने डाउट्स। आई
हाँ जी,
थिंक
हाँ
ही
जी।
विल बी एबल टू हेल्प।
अच्छा मैम, जैसे जैसे हमने नॉर्मल कंपोजिट का मतलब कोई सैंपल टेंसाइल टेस्ट का सैंपल कटिंग कटिंग करना है, तो उसका स्टैंडर्ड कैसे, मतलब कैसे डिसाइड करूंगा कि 3 mm रखना है थिकनेस, या 4 mm थिकनेस रखना है, या 6 mm थिकनेस रखना है? अब बहुत सारे स्टैंडर्ड है मैम उसमें गिवन, तो कैसे मतलब डिसाइड करना कि मैम 3 mm थिकनेस का सैंपल कटिंग, मतलब सैंपल मैं प्रिपेयर कर रहा हूँ, बना रहा हूँ?
हम लोग तो एक स्पेसिफाइड वही यूज करते हैं, जो हमारे लैब में पहले से हुआ है। एक मिनट में मैं चेक कर लेती हूँ कौन कौन से
अच्छा।
मतलब मेथड्स यूज होता है, स्टैंडर्ड्स।
हाँ मैम। हाँ मैम, मैं क्योंकि मैं अभी अभी स्टार्ट ही किया मैम, मैंने काम अभी कंपोजिट का मतलब बना सैंपल बनाने का, तो
हम्म
फिर मैं अब आगे टेस्टिंग के लिए मतलब सैंपल कटिंग करने है उसके लिए पूछ रहा था। कि वो डॉग वन वाला, जो डॉग वन शेप वाला टेंसाइल टेस्ट होता है, मतलब शेप होता है,
हम्म
उसके लिए भी मतलब कटिंग करना थोड़ा मतलब कोई आसान तरीका मिल जाता। मैम आपका काम भी कंपोजिट पे ही है, नेचुरल फाइबर पे है क्या?
मेरा काम हाँ कॉम्पोजिट का ही है, ग्लास फाइबर और कार्बन फाइबर के ऊपर है।
अच्छा ठीक।
हम लोग आईएसओ 527-4 यूज करते हैं टेंसाइल टेस्ट के लिए।
5
527-4, 5 आईएसओ 527-4।
527।
हाँ।
अच्छा।
ಹೇಳಕತ್ತಾಲೆ
और मैम ये इम्पैक्ट टेस्ट के लिए करना है और फ्लेक्सुरल टेस्ट के लिए करना है, उसके लिए भी मतलब क्या?
फ्लेक्सुरल टेस्ट का आई थिंक आईएसओ 178 होता है, बट इम्पैक्ट टेस्ट का मेरे को अभी आइडिया नहीं
ये
है।
आईएसओ होता है या एएसटीएम होता
आईएसओ।
है? आईएसओ है। ठीक है मैम। फर्दर मतलब हेल्प के लिए आपके आपको व्हाट्सएप नंबर मिल पाएगा मैम, कोई प्रॉब्लम पूछने के लिए?
मेरा मेलिंग एड्रेस होगा शायद, नहीं है?
मैम है नहीं मैम, नहीं है नहीं मैम, ईमेल।
एक्चुअली सेशन में मैं
क्योंकि वो
अपना
एन पे जब हम
पर्सनल
मेल आता है वो
इंफॉर्मेशन नहीं दे
एनपीटी।
सकती हूँ, क्योंकि ये सेशन यूट्यूब में जाएगा।
अच्छा ठीक है, ठीक है, ठीक है, थैंक यू। ठीक है मैम, ठीक है मैम।
आप एक काम कर सकते, आप अपना ईमेल आईडी मेरे को दे दीजिए, मैं उस पर मेल कर दूंगी।
हाँ जी,
आप
हाँ जी, ठीक है मैम।
ये साइड में कमेंट सेक्शन में अपनी ईमेल आईडी लिख दीजिए, मैं आपको मेल कर दूंगी।
हाँ, ठीक है मैम।
हेलो विनोदा, आई थिंक यू आर लेट टुडे।
मैम
हाँ
मैंने भेज दिया, सेंड कर दो।
हाँ हाँ, मैं उस पर आपको मेल कर दूँ।
ठीक है,
हेलो विनोदा, am I audible?
थैंक यू मैम।
Okay, welcome.
हाँ,
Vinoda, am I audible? You joined late today. So, do you have any doubts?
थैंक यू। मैं एंड कर दूं मैम,
हाँ
एंड कर
अंकित जी,
दूं?
हाँ, if you don't have any doubts, you can leave.
थैंक यू मैम।
Okay, welcome.
Yes, ma'am.
Ah, hello Vinoda. You are late today, I
Yes,
think.
yes. Sorry, ma'am. I forget at that one. I came office late, so that's the reason, ma'am.
Okay, so do you have any doubts for assignment too?
No, ma'am. You go ahead. If there any, I will let you know.
Okay, then I will repeat the presentation once for you then. Okay.
No, no, no problem. Thank you.
Like sample questions that I have, I already discussed the sample questions.
Yeah.
So I will discuss like a fast run with you, so you can see
Yeah.
them, and if you have doubts, you can ask me.
Okay, ma'am. I will check the video. I will let you know.
Okay, so you want to do it later, or I can repeat it for you right now also, because slot timing is from 6 to 8, so there is another 1 hour.
Okay, ma'am. Okay.
Okay, then I will repeat once for you.
Okay.
So the first question is, in generalized Hooke's law, stress equal to C ijkl into the strain in the KL, eta KL, where ijkl is equal to 1, 2, 3. So this C ijkl is, options are A, second order tensor, option B, fourth order tensor, option C, 6 cross 6 compliance matrix, or option D, 6 cross 6 stiffness matrix. So uh, the compliance or the stiffness matrix that we get are from 9 stresses and 9 strains. So this gives a relation between 9 stresses and 9 strains. So the number of correlations between this stress and strain will form 81 independent constants. So this 8 as the uh, this tensor is defined as 3 to the power the n number, where n is known as the order of the tensor. So if the n is equal to 2, that is if the number of components in that matrix are 9, so that is the second order tensor. Similarly, if there are 81 components like this stiffness matrix, so that will be 3 to the power 4, so a fourth order tensor. So that's why this stiffness matrix is a fourth order tensor. So option B is the answer. यश को बोल रहे थे. Question number 2. So match the following. First table is the type of materials. The second is the number of independent elastic constant. So the types of materials are isotropic, anisotropic, monoclinic, and orthotropic. And number of independent elastics are option A 21, B 9, option C 2, or option D 13. So when sir taught in the class, so number of independent elastic constants were initially 81 for 9 stress and strain components. So we were initially given, we got 81 independent constants. But then comes the concept of shear symmetry. Shear symmetry, that means the component and the shear in xy direction will be equal to the shear in yx direction. Similarly for other coordinates. So from shear symmetry, the number of independent elastic constant decreased from 81 to 36. After that came the concept of symmetry, that the constants like which has this direction like 1 3 will be equal to the constant value in direction 3 1. So from the concept of symmetry, the number of independent constant reduced to 21. Now this number, 21 number of independent constant, this matrix shows us the matrix of an anisotropic system. So anisotropic is when the properties of the material are different in all the directions. So for that, the number of independent elastic constants will be 21, option A. After anisotropic comes monoclinic, where one of the there is one material property symmetry. So what they, like suppose there is a plane of symmetry in direction xy. So in z and z dash there will be symmetry in the properties. That calls a monoclinic material, and it will have further 13 number of independent constants. After monoclinic comes orthotropic, where orthotropic has three planes of materials which are symmetric. So here the number of independent constants will decrease to 9. And finally, after orthotropic comes transversely isotropic, where along with orthotropic, one of the planes is isotropic. So the properties in that plane will be constant. So that will decrease the number of independent constant to further 5. And finally, there is isotropic material, which is only two independent constants, which are either Young's modulus or Poisson ratio, and there is already a relation between the shear modulus, Young's modulus, and Poisson ratio. So any two of those components, if we know, we can find all the three values required for forming the stiffness or the compliance matrix of an isotropic material. So here the option will be option B. Next question, question number 3, is that in the stress-strain relation of a fully anisotropic material, which of the following is true? So this is, there are different sections of a stiffness or compliance matrix, which are named like this. You can see extension terms are those which gives direct relation between stress and strain. Extension coupling, which gives the relation between a stress in one direction and with respect to that what will be the strain in other directions. Then comes shear, which is direct relation between the shear stress and shear strain in certain direction. Shear coupling gives the relation between the shear stress and shear strain with respect to one point to other directions. And then lastly, there is shear extension coupling, which gives us relation between the shear values and the direct normal stress and strain values. Okay, so we have to get the whatever material they have talked about, either fully anisotropic, orthotropic, transversely isotropic. Just get their compliance or stiffness matrix. Then you have to equate that matrix for values with different different areas of this matrix, and we can solve this answer. So for a fully anisotropic material, you can see all the independent constants are non-zero. So option D will be the answer, that all the extension, shear, and shear extension coupling terms are non-zero. Whereas if it's an orthotropic material, you can see this portion, which is the shear extension coupling term, are 0, and also the shear coupling terms are 0. So here all the shear extension coupling terms are 0. So this one is the only correct answer here. So option B is the correct. Similarly, for isotropic material, you can see the shear extension coupling terms are 0, and this shear coupling terms are also 0. So here we have to find which of the following is not true. So here the first option, they're saying that all the extension coupling terms are 0. Extension coupling terms are this one. These are non-zero. So this option is the incorrect one. That will be our answer. Now in the stiffness matrix and compliance matrix, the diagonal terms are, options are A, always negative, always positive or negative, can be positive or negative, must be always positive, or are positive in stiffness matrix and negative in compliance matrix. So the diagonal terms of this matrix are the direct relation between the stress and strain. What does this mean? That if there is a stress in direction 1, then it is the correlation between the stress in direction 1 and the stress in direction and strain in direction 1 that is related by this diagonal terms. So if displacement is given at a certain node, then the action at that node should develop in the direction of that displacement. That is why the mean diagonal elements in the stiffness matrix will always be positive and cannot be negative at all. So option C is the answer. Now for an isotropic material, the Poisson's ratio mu is bound as. So this comes from the notes sir talked about the restriction in engineering constant. So when we consider the shear and hydrostatic loading on certain material, so there are these equations. First equation where we can find the shear modulus with the help of Young's modulus and Poisson ratio. From equating this value, we can say that the mu value should always be more than -1. And the second equation is the value of finding the bulk modulus. So for having the positive bulk modulus, the value of mu has to be always less than 0.5. From these two conditions, we can say the Poisson ratio is bound between -1 and 0.5. That will be the answer. The next question is a simple one where transversely isotropic materials have three orthogonal planes of material property symmetry, and we know that the third, it has one of the plane of material property isotropy. So that's what distinguishes the transversely isotropic material, that it has already orthotropic material property, along with that one of its face is isotropic. So option B is the answer. Now here they are asking that with respect to Cartesian coordinate xyz, the state of stress at a point in an orthotropic material is. So our conditions are given that there is a stress in x direction which is non-zero and all the other stresses are zero. So we have to find what will be the strains induced. So first we have to see which material they are talking, that is orthotropic material. For orthotropic material, this is the compliance matrix which gives the relation between strain and stress. So we know the stress in x direction or 1 here you can see is non-zero and all of these values are 0. So with that we can find what will be the value of strain. So strain in direction x will be non-zero as this constant is non-zero. Similarly, because of these two constants being non-zero, the strain in 2 and 3 direction will also be non-zero. But here the shear strains will be 0 because these coefficients are 0. And when we equate it, multiply it with the stress, we will get the shear strain equal to 0. So from that observation, we have to choose the option which is correct. That is option C is the correct one. Similar question here, they are asking about an isotropic material. So this is the compliance matrix of an isotropic material. So here all these values are non-zero, are 0, and this is the only non-zero value. So from the coefficients, we can see the strain in x, y, and z direction will be non-zero, and the shear strain in the all the directions will be equal to 0. So option D is the answer. Now orthotropic materials are characterized by option A, 3 Young's modulus, 3 Poisson ratio, and 3 shear modulus. So this is the correct answer. So we should always remember this, that mostly all these compliance matrix and stiffness matrix are independent constants whose values can be found from the engineering constants. So the engineering constants that we use are Young's modulus, Poisson ratio, and shear modulus. So this will be in all the three directions. Accordingly, there will be 3 of all these values. So these values can be found by uh, uh, experiments and testing by using an UTM. And also in the class, I have already shown a UTM. Maybe after the class, after this questions are solved, I can show you also. Okay, so this will be the answer. The last question is, a specimen made from an orthotropic material is tested along perpendicular direction 1 and 2 in UTM to obtain Young's modulus and Poisson ratio, and the following data were obtained. So E1 equal to 200 gigapascal, E2 equal to 20 gigapascal, mu12 equal to 0.3. So we have to find the possible value of mu21. So with the equation of symmetry, so the coefficients Sij will be equal to Sj1. So from these, the equations in terms of engineering constants, when we equate these coefficients, we can get this final value, that is mu21 by E2 equal to mu12 by E1. So we have to always remember this. So by using this equation, we already know the value of E1, E2 and mu12. So we can find the value of mu21, that will be equal to 0.03. That is option. So any doubts in these questions? Vinoda?
Ma'am,
Ah, yes.
hello. I'm audible.
You're audible.
Ma'am, these are questions I don't have no problem. I want one question, ma'am. How to calculate the volume fraction and volume fraction of the resin and fibers? Then you let me know, ma'am. Any know?
That will be discussed in the next class. I think the third module has the formula and all for volume fraction.
Theoretically, how to find that I don't know actually.
Theoretically, they are explained in the class, and experimentally, you need to do the ignition test.
Yes, yes, yes.
Like you have to burn it and see the change in the mass.
Okay, okay, okay.
So you work with composite?
No. Yes, yes, yes. I'm working with composite and total 5 years of experience. Matrix and reinforcement. We are making formulation like that. Epoxy and reinforcement carbon fiber and taupreg filament turning like that.
I think in next modulus, sir has already discussed the analytical method of finding the volume fraction and all. Maybe in next assignment questions, I will be discussing that. I have to check
Okay.
which modulus they have, but I think in the next module only they have that. But
Okay, ma'am.
sir has that in his
The
course.
okay. Then related to composite, could you suggest me which who's the writer for the like reading for books like composite related reinforcement or matrix related books?
Books are they not given in the site? Any like there will be references of different books in the site when you will go to the course. Sir has already given some references. You can see them,
Okay, okay,
or you can. I think you can mail some TA or in the discussion about which books will be good. But sir has given some references. Wait, I can check.
okay, okay, okay. No problem.
You can check it
You're
there.
not well, no?
Huh?
Not well.
Okay, so any else doubts? Any more doubts? Okay, Prajit Mitra, you came very late. I almost ended this session twice. Prajit Mitra, am I audible? Okay, then I will end the session here. Okay, Vinoda, if you have no doubts, then we'll meet in the next class. I'll be discussing some sample question for assignment number 3. And I will see
Okay,
our
ma'am.
volume fraction. If sir has not taught in the module 3, then I will put a separate slide and explaining how to find it. Okay,
Okay, ma'am. Then one
okay
more
then.
thing, ma'am.
Huh?
One more thing. In the laminate, we are building the one laminate. So how much percent of the volume resin percent and how much of the reinforcement percent is it is good for composite building the laminates?
Uh, Actually, it depends on the manufacturing method you're using. Like there are some manufacturing method which can give you volume percent, like maximum volume percentage of fiber you can get achieve is around 0.6. More than 0.6 is very difficult. So around 0.5, 0.6, if you're like using filament winding, like what we have done filament winding, we got around zero point 0.4. So zero point 0.4 was the maximum fiber volume fraction we could achieve. So above that, there are other method, I think autoclave method or something, which can achieve more than that. But basically above zero point 0.4, 0.6, it's very rare to get a fiber volume fraction more than that.
Okay,
So
okay,
zero
okay.
point 0.6 is also kind of like an idle. 0.34 is will give you a very good and strong composite
Okay, remaining thing is matrix, all the
matrix.
percentage.
It is matrix. Like point point 4 is volume fraction of the fiber. So reinforcement is 40%, 60% is matrix. Like
Okay, 60% of the matrix. Okay. Then we will get the properties, good properties. No?
you will get good property. Like filament winding, I work on like filament winding. So there, zero point 0.4
Okay,
we assume as like a normal and very good product. If we get a volume fiber volume fraction of zero point 0.4. Okay.
okay, okay, ma'am. Okay. I am working also pre-preg and in the pre-preg we are making the laminate. So is there 50% of the fiber wall production and 50% of the resin factory. So two types of we are done and some properties are changeable. Mm, okay, ma'am. Uh,
Okay then.
uh,
Do you have any other doubts? Maybe I can discuss them in
no,
next
no,
class.
no, ma'am, no, no problem.
Okay. Okay then. Thank
My
you.
side is over.
Okay.
Okay, thank you.
Thank you. Then I will end the session here. Okay. Thank you. Prajit Mitran, are you still there? Okay, he left.